Hello everybody, I am Kent Mayhew and my website is newthermodynamics.com, and this is part of the YouTube site New Thermodynamics. Okay, and today we're going to talk about the latent heat and its probability function. Now, in our previous video called Boiling and Lost Work in Simpler Terms, we described the latent heat of vaporization, okay, and basically we discussed that at the boiling point the liquid's temperature remains constant, dT equals constant. The latent heat is then equal to the change in the system's energy plus the work done on the atmosphere, which is equal to the change in the bonding energy of the system, du system, plus the work done to the atmosphere. Okay, so if you want, you can go and look at that video before proceeding with this one. If you don't understand that video, then we'll proceed here. Okay, let's just consider the bonding in a bulk liquid for a second. Okay, in Cartesian space, there are three orthogonal directions in which a given liquid molecule can be bound to its neighboring molecules. Hence, we consider a liquid molecule in a bulk liquid has 6 electromagnetic bonds, or, you know, in the case of water, the dipolar bonds. Okay, and it's in 6 directions, plus or minus x, y, and z. Okay, and the mean kinetic energy plus potential energy of each molecule is 3 kT. Okay, this is based upon kinetic theory, whether it be mine or the traditionally accepted one. And 3 half kT is the kinetic, and 3 half kT is the potential. Okay. Previous slide we discussed that the mean energy of each molecule in a bulk liquid is 3 kT, right? That was 3 halves kT plus 3 halves kT for kinetic and potential. So in any direction, the mean energy that can be passed is accepted as being kT, and kT being the mean accessible energy that a liquid molecule can access from one of its bound neighboring molecules. Okay. Now, the thought of passing an energy of kT in any direction has led to the Boltzmann's exponential, which is the exponential of the energy required, negative of the energy required over kT, and kT being the energy that can be passed. Okay, so now we apply a proportionality constant, and we get the probability of a given molecule obtaining energy E from one of its neighbors, as written up top. Okay, the probability constant B can be determined by the normalization condition. Okay, and that's the probability approaches unity, or 100%, as kT approaches E. It often turns out that the proportionality constant is considered to be 1. Okay. Now this has led to the poorly conceived traditional assertion that the probability of vaporization and or boiling on a per molecule basis can be written in terms of the 2 equations below. Now the one on the left is written in terms of the latent heat per molecule, negative L, a liquid going to gas, and the other one on the right is written in terms of the enthalpy per molecule, and a lot of people like to consider it as enthalpy. I'd rather do latent heat, and because there's certain questions that have to be done with our traditional understanding of enthalpy. Again, I'll start off by writing the probability on a per molecule basis. Okay, we can equally write it on a per mole basis, as is done in the 2 equations below. Basically, negative L is now the molar latent heat, and the one on the right is molar enthalpy. Okay, and they're both divided by the ideal gas constant and times temperature. Okay. But consider water now, okay? If we do the ratio of the latent heat versus the energy that can be exchanged, you get 13.1 as a ratio. I mean, it doesn't make sense that the latent heat of vaporization for water is 13 times the mean accessible thermal energy that can be exchanged between 2 molecules, okay, when water is at its boiling point. To emphasize the point that it doesn't make sense, just consider a solitary package of accessible energy, kT, from one of the neighboring molecules, okay? And to have the energy required for vaporization, then the water's temperature would need to be 4,891 degrees K, okay? And this can be shown by calculating the temperature from the above equation, okay? And of course, water boils long before it ever reaches anywhere near that temperature. So does it make sense to just consider that the bonding energy is in 6 directions, while the energy required to break the 6 bonds is obtained from just one neighbor? I mean, would logic not dictate that 6 neighbors can all provide the energy required to break the 6 bonds at a given instant? Right? Our probability would now become this. The 2 probabilities shown below, the top one per molecule and the bottom one the molar. Okay? But however, the probability still isn't perfect, because just consider for water, we still have the ratio of the latent heat to 6 RT being 2.2. We start by reiterating that the ratio of the latent heat to the 6 times the energy that can be passed in any one direction is still 2.2. So the question becomes, is this due to the bonding energies? Okay? And so let's investigate 3 noble gases whose temperatures are somewhat above absolute zero. Okay, so for argon, we have the ratio of 8.8. For krypton, we get the ratio of 9. For xenon, we get the ratio of 9.3. It's sort of interesting. Can we surmise that there's a kinetic number 9? Right, if you want the ratio, 9. Okay, let's look at a plausible path for the kinetic number 9. Consider that all 6 bonded neighboring molecules can pass all of their mean kinetic energy. Okay, that's 3/2 kT over 2. That's in from 3 directions onto a vaporizing noble molecule. Okay, thus breaking the 6 bonds. Hence, you get 9 kT. Sort of interesting. You know, and now the vaporizing molecule still maintains its kinetic energy at 3 kT over 2 for when in the vaporous state. As mathematically eloquent as this is, I remain unconvinced, as it certainly goes against the traditional assertion that the mean energy passed in any one direction by a solitary molecule is kT. Okay, so we don't really know, but it's interesting to envision the path here. Okay. However, I mean, the kinetic number 9, there's more than one plausible path. Okay, so let's take a look at a multi-step path. It can be equally envisioned that the path is actually a 2-step process. Okay, such as all 6 neighboring molecules pass all their mean kinetic energy plus potential energy in one direction, kT, onto the vaporizing noble molecule, thus breaking the 6 bonds at some instant. Plus the vaporizing molecule's mean kinetic energy of 3/2 kT, hence we have 7.5 kT to break the bonds. And then in step 2, the vaporizing molecule collides with the bulk liquid and attains another 3 kT over 2, thus attaining 9 kT. Again, as plausible as this may be, I remain unconvinced. Importantly, we have shown how one might contemplate a 2-step or a multi-step evaporization process. You know, and by this I mean we've defined the path. As a human, I'm far from perfect, and I just do not know the real answer to this. I mean, I have played the game of trying to determine the path in my mind on several prolonged equations, and have arrived at the conclusion that beyond the realization that all 6 neighboring molecules must contribute to the energy required for evaporation vaporization, I remain unconvinced of the path. There could be several paths that occur, okay? In my paper on this subject, okay, which was published in 2013 in Physics Essays, as listed below, and in my books, which were published later, I have described different plausible paths, and at times I even thought that perhaps the kinetic number was 8.5 rather than 9. Okay, and I'm still not sure. Okay, input from others would be really appreciated. However, I got to emphasize a new, more recent realization. So we'll leave the probability function for a few minutes here and we'll talk. Okay, it is accepted that the linear functionality of heat capacity does not hold as temperatures approach absolute zero. Okay, now I don't believe that in the least. Rather than the above being the case, I now consider that it's actually the linear functionality of the parameter temperature that does not hold as temperatures start approaching absolute zero. And this specifically means that as a system's thermal energy density becomes increasingly less proportional to temperature, the closer a system gets to absolute zero. Okay, and this is really no different than when we start talking about high temperatures such as a blast furnace. If you think about it, at high temperatures, we know that the energy density is related to temperature to the fourth. Okay, so there's no reason to expect that the temperature as we approach zero should be proportional to the energy density as it is in most temperatures we experience here on Earth. Okay, this will be discussed in chapters 5 and 17 of my new book, which will be it's rewritten and it'll be out shortly. And I also comment about it on my website, http://www.newthermodynamics.com. Okay, now you must realize that when I say temperature is no longer proportional to the energy density within substances as we approach absolute zero, the reason is based upon the black body curve. Take a look at the black body curve below for temperature 5800. That's sort of the temperature of our sun, okay? You can see that peaks around in the visible, okay, and then it drops off, okay? Now, thermal energy within matter is mainly in the infrared, with the strongest emphasis being in the thermal infrared. And thermal infrared starts at 3000, which is on the far right of this diagram, and extends all the way to 100,000, which is not shown. But you can imagine how linear that is, okay? And if you actually think about it, because of the large breadth of wavelengths, there's a lot of energy contained within there. Actually, more than is contained on the left-hand side of the graph if you do the quick calculation. Let's reconsider generalities of black body radiation. As one approaches absolute zero, the most likely wavelength, as defined by Wien's law, becomes longer and shorter frequency. Okay? And so if you take a look at the graph below, where for T equals 3, which is on the right, 3 degrees Kelvin, you can see that we're now into the microwave and we're getting out of the far infrared. Okay, so the microwave is no longer really thermal energy in the same way that the thermal infrared was. Okay, so you can imagine that temperature itself would no longer be proportional to the energy density of a system. Okay, and I believe that the energy density would no longer be a linear function of temperature as one approaches absolute zero. Moreover, I think this will start becoming apparent around 250 K, and it becomes blatantly obvious as temperatures drop below 100 K. Let's reconsider the kinematic number again. Okay, and again we look at the ratio of latent heat to the energy that can be exchanged. Okay, now if you realize how accurate would the determination of a liquid's or a gas's energy be based upon a KT relation at low temperatures? It doesn't make sense. The accuracy now diminishes. So this may also befuddle our determination of the possible kinematic number. Remember, the noble gases, their boiling points that we discussed were between 100 and 165 degree K. Okay, and if we start to lose the correlation between temperature, the linear correlation between temperature and energy density around 250 degrees, this means that the kinematic number may be higher than we think, okay, or than my quick analysis indicates. And so by being higher, it might be 9.5 to 10.5. I just do not know. It's interesting that kinematic number of 10.5 is implied by the Troughton's law, okay? And you can look up the Troughton's law if you want. We won't discuss it here. But there's plenty of food for thought. Okay, now let's return to the proper probability. Okay, the probability of vaporization should approach unity, P approaches 100, as a liquid's temperature approaches its boiling temperature, T approaches TB. Or if you prefer, when the bulk liquid reaches its boiling point. And this is in terms of its boiling temperature and boiling pressure. Okay, the probability should now be written in the following form. One may wonder, what is the so-called constant B now? What can be envisioned as the likelihood of the necessary path being followed, i.e. the 6 neighbors all passing the sufficient amount of energy onto the vaporizing molecule at some given instant. Without B, that all remaining liquid molecules would vaporize at the same instant when the liquid reaches its bulk, or when the bulk liquid reaches its boiling point. Okay? So you can consider that, again, the Brownian motion in bulk liquids, they vibrate around 10 to the 13th times per second. Okay? So you can imagine this probability plays out so many times in each second. And it's only when the 6 molecules are passing the energy on to the vaporizing molecule at the same instant can it break all the bonds and become a gas or a vapor. Examine the new versus traditional probabilities. And I write the new one on the left here and the traditionally accepted one on the right. Okay, and it's written in both latent heat, in terms of latent heat, and in terms of enthalpy. How did this mistake happen? You got to realize that the rate of vaporization is related to the probability of either a single or a mole of molecules evaporating multiplied by some normalization factor and the liquid's concentration. Okay? So basically we get our new vaporization rate on the left here versus the traditional one on the right. Okay? How did the mistake happen? It must be understood or stated that one can readily use the wrong energy and the wrong probability function and then apply it to some experimentally determined rate or data and still normalize their data to match the wrong equation. Okay? And so now you can imagine the normalization process of experimental data allowed us to use the wrong equation, which is given on the right for the rate, instead of the proper equation, which is given on the left, and in terms of the boiling temperature versus the temperature of the liquid. Okay? This happens too often throughout thermodynamics. Probably the most often it happens is in the poorly conceived Clausius-Clapeyron equation, which gives us the vapor pressure as defined by the following equation. Now, I have determined equations that are similar to the Clausius-Clapeyron equation in my book, and it's derived from first principles. Okay? And basically, you can now begin to understand why we made these mistakes. Okay? Because the Boltzmann's exponential is such a powerful equation, and yet it's got the big Achilles heel of being able to use the wrong equation and normalizing your data. Okay? And that is a big issue that's not accepted in thermodynamics. Let's discuss the normalization factor for a second here. Okay, now we've got the proper or the good equation up there in terms of temperature boiling over temperature for the vaporization rate. Okay, so the normalization factor N can be thought as defining the rate of occurrence over a given time frame. Okay, so you can imagine the liquid is at its boiling point. Hence, from an energy perspective, all the bulk liquid's molecules could vaporize. But you need the 6 neighbors to be acting all at once, okay, in the right form, fashion, or the right path. Okay, certainly there's a probability of one or more neighbors having the required accessible energy, but the other neighbors may have some different values, some lesser values, or something like that. So the combinations and permutations become endless. And you can really think of N as being part of the combinations and permutations that prevent the liquid from all boiling at once. Okay? Continuing discussing the normalization factor. It is dependent upon all sorts of variables that define a system. Therefore, for any one value of N in any two systems to be identical, both systems need to be rather similar, very similar. And scientists sometimes get this wrong. As they'll write that the N is some universally applicable constant. It is not. It is only constant for similar systems. Okay? And the most important thing to remember is as the pressure increases, N should decrease. Okay? You can think of this as a reduction in the rate of vaporization due to an increase in the physical constraints upon the given liquid molecules. Okay? Hence, we can write N is really a function of pressure, as we do. Okay, to improve this actually improves our understanding as to why liquid's boiling temperatures will increase with increasing pressure. You can imagine, as we increase the forces of constraint upon the liquid molecules, then the energy required for vaporization must increase. And I end the slideshow with discussing my book, New Thermodynamics, Say No to Entropy. I want to express that I'm rewriting it for the 3rd time, namely because I've had some new insights, okay, and the new book will probably be called New Thermodynamics, Goodbye to the Second Law. The realizations have changed things like Chapter 4, so I'm sorry if anyone bought it. You can get Chapter 4 online from my website, www.newthermodynamics.com. Most of what I've discussed here is in my books and in my website. Okay, also on my website you'll find my peer-reviewed and other papers. I do apologize for my odd mistake, as they certainly exist, and I guess I'm really apologizing for being a human being. Okay, accordingly, any help and or improvements or commentary is always appreciated.